All right, folks, so there's a lot going on. I wanted to check in. So the course is kind of speeding up a little bit in terms of the work. I think the course is actually maybe slowing down a little bit in terms of the number of new concepts that you're being exposed to in every lecture. So that's my thought. So this is the phase where it's like kind of about banging out assignment 3, all these practice assignments, as well as just starting to shore up understanding of actual material. For those of you that haven't looked at assignment 3, there are 2 parts, or 3 parts technically, but the first 2 parts of the assignment are what I would consider to be warm-up. Like, we give you an algorithm, you're supposed to write it in CUDA just to kind of start learning some mechanics of how do I get this code to compile, how do I create some threads. The real part of the assignment is the last part, which is the render. And unlike most other systems classes, this is about coming up with a performant implementation, sure. But it's also actually about coming up with some algorithms that will make this work, they'll actually allow you to parallelize this thing. And I figured I'd spend 5 minutes actually just kind of taking everybody through the problem that you're having to solve. So the problem that you have to solve is actually to render a picture. Here are some pictures, or these are low resolution, but you'd render like a 1,000 by 1,000 image that looks like this. And to keep things simple, since this isn't a computer graphics class, the only thing you can draw in your pictures are a bunch of circles. So I basically give you the center XY position, the radius, and the color of large numbers of circles. And so all of these images, if you look at, are just images of circles. And the main loop of how to do this is actually pretty simple. Go through all the other parts. It's actually pretty simple. If you look at it, is let's ignore the front part where every frame the circles can move. So ignore that. But here it's quite simple. It's for every circle that I give you, compute the bounding box of the circle. So if I gave you the position and the radius, you can compute the bounding box. And then given the bounding box, iterate through every pixel in that bounding box. And if the center of the pixel is inside the circle, you update the color of the pixel accordingly, according to the color of the circle. That's like the world's simplest drawing algorithm for simples. Now, the challenge is that it's not these circles, if you look carefully in my picture, are actually somewhat transparent. So it's kind of like a piece of stained glass or something like that. So a 50% transparent red circle on top of a blue circle looks different than that blue circle on top of the red circle because of transparency. So the thing that makes this problem goes from incredibly trivial to incredibly interesting is that I'm going to give you the circles in an order. I'm just going to give them to you in an array. And I want you to assume that they're ordered in like sort of back to front order. So in other words, you have to add in the first circle before you add in the next circle, and so on and so on. So that's the ordering constraint that actually makes this a tough little problem. And just to give you a sense of that is here's an example of blue over green over red. So if you kind of look carefully, like the blue is the first piece of of a filter. Here's if I combine them together in some other order. And you just get a different result. So we're going to call that wrong. Okay. So the name of the game is, if you just look at this nested sequence of loops, sequentially, this is a valid algorithm for each circle in the order that they are in the array. The thing that you would probably do, and the code that we give you to start, parallelizes this loop. For every circle in parallel on a different thread, just carry this out. And that will compute the wrong answer. Okay? So step 1 is to confirm to yourself that computes the wrong answer, and then make a change, right? And when we talked in the data parallel thinking class, we talked through some various possibilities. This is very similar to for every particle, what bin is it in? And the key thing to keep in mind is that even though you're supposed to process all these circles in the order that they appear, the only way that you can get the wrong answer is if you process them in the wrong order and they overlap. Because if they don't overlap, it doesn't matter what order you process it in. So that's all I'm going to do to set up the problem right now. But step one should almost certainly be change the code to get a correct answer. And that correct answer will be parallel, but very slow. And then you're going to chip away at correct, parallel, and fast. So that's the sort of the sequence of the assignment. Okay? Or in other words, if you knew for every pixel what circles possibly overlapped it, you'd basically be done. Like if you had this magical data structure of for every pixel on screen, here's a list of circles that might overlap it, you would basically be done. Because you know you can process every pixel in parallel and do that safely. That's all I'll say on the assignment. It's a fun one. I think most people really, really like this. That was either a sarcastic laugh or a laugh in agreement. Okay. Since Kunle is away on some business travel today, the reason why efficiently evaluating DNNs is at this point in the lecture schedule, we're not continuing on with some other stuff, is largely just for scheduling. So this is a lecture that will be very useful to you in assignment 4, so it's coming a little bit earlier than it needs to be. But in general, I thought that it might be fairly interesting to folks, given that everybody's messing with various forms of deep neural networks today. I'm going to talk a little bit about how we efficiently optimize these things in the context of running deep neural networks on modern GPUs and CPUs. I will hint at the very end of the day about all of the interesting specialized hardware for DNN acceleration that is starting to emerge, but I'm going to save that to the lecture on specialized hardware, which I think is right before Thanksgiving, if I remember. So today is going to be about mapping DNNs to GPUs and CPUs. Okay. Quick just survey of what folks know. How many people have taken a class where you have had to execute or implement or use modern deep networks? That number keeps going up every year, so we're getting closer and closer to almost everybody in the class. How many people, there's actually another class this quarter by a new faculty member here. She's teaching this great class called 229S, right? Do we have any people in that class? Because there might be some overlap here. And so either this is going to be review or this is going to be very helpful. We'll see, actually. And so, I probably need to coordinate a little bit more next year, but I didn't know she was teaching that class. So anyways. So I want to just start with, for those, the small fraction of you that have not seen any deep neural networks, I'm going to get into the workload a little bit because I need to make sure everybody's familiar with the workload. And I want to do that for two reasons. One is I think I'd like to give everybody a base, like a basis of how to think about things. And really, we can think about things in a systems class without much math at all. And that's going to be very helpful. So here's a question. You've seen dependency graphs before in this class. Like we saw this when we talked about superscalar execution. Or, to be honest, if I gave you this task graph, you would know how to execute it right now. So what does this code do? I mean, it's just an expression. But let's look at it a little bit more carefully. Like it maps to basically what I've done here, right? Like I'm basically computing the product of some values, and I'm summing them. And if you look carefully, that's actually just a dot product followed by a max on the value of that dot product. Okay. And if you took like an early deep neural networks class, you would see a diagram that looks a little bit like this. They would call this like a neuron in a modern deep neural network. And at the end of the day, it's just a circuit that performs an operation like what I put on the previous slide, where inside this neuron there's a set of weights, which is just a vector. We don't need to think about the meaning of those weights at all at the moment. And there's some input, an input vector here, which is, in this case, a 4 vector. And the output of this neuron you should just think of as a function which performs a dot product between two vectors. Optionally actually has a bias or an addition of another vector, and then takes that through some nonlinear function, and that doesn't really matter at all either. And the function that I'm going to use in this class is called a max. If you took a deep learning class and wanted to feel better about yourself, you'd call it something like a rectified linear unit, but it's a max in this case. Okay. So for the sake of this conversation, we can think about what we're interested today is taking, sort of this overall computation, which is this nonlinear function f, on essentially a big matrix algebra operation, in this case a dot product, and repeating that over and over and over. So, you can think actually about this neuron as actually being, you can think about every one of these little neurons as being a little binary classifier if you want to take a machine learning interpretation of that. Like if it's above 0, it's saying yep. If it's below 0, saying no. And now let's just start wiring them up, because we're computer scientists. I have a little function, and I can wire a simple function up into larger functions. And often these networks are arranged in a fairly regular way, and that I'll have some number of these at every layer, and the layers are defined by saying like the output of all of this layer turns into the inputs of the next layer. And if you look carefully in my diagrams on the left, you see an example of a fully connected layer, meaning that every single output from layer I is an input to layer I plus 1. On the diagram on the right, you'll see something that's not a fully connected layer. It's actually a convolutional layer in 1D where there's like the sliding window of every 3 inputs in this case go to the next neuron. Okay. All right. So let's write this a little bit differently. Let's write this instead of these visual diagrams. Let's write this as some more in a linear algebra notation. And just keep in mind that, see here I have 4 neurons. So I have 4 sets of, or I guess in this case I have 3. Yeah, I have 4 neurons, and so I have these different sets of 3 weights. So in this case, my neuron has actually got 3 weights in it. Excuse me, my original diagram had 4, but this is a neuron with 3 weights in it. So for every one of these 4 gray boxes, there are 3 weights. The input, notice that there are 3 input values. That's the right-hand side vector x. And then the execution of computing the output is just a matrix vector product here. Okay? And of course, that goes through that nonlinearity f in this case. So all of these, some fancy diagrams start boiling down to dense matrix algebra pretty quickly if you want to think about it like that. Another way you can think about the exact same thing is more like this. So this is a convolution. So if you look carefully at this C code, there's an input image, which is width by height. It's actually width by height with +2, just for some boundary conditions. The output is a width by height image. I have these weights, and for every pixel of the output, I do something that involves surrounding pixels of the input. And if you take a look at this code, and I asked you, what does it do? Some of you might say, oh, it performs 2D convolution. And then I turn right back around at you and go, well, what the heck does that mean? Right? And so if this was, let's say, an input image, what does the output image look like? Blurry. It's blurry, right? Because every output pixel is essentially the average of the surrounding pixels. So imagine a situation where I had a white input pixel and really dark colored surrounding pixels. The convolution is going to bring that white pixel down to the average. And around that pixel, it's going to bring those black pixels up to the average, right? So if I run this code, on an image that looks like this, you'll get an image that looks like that. That's one example of a convolution, okay? Right. So that was our 3D image convolution. And I just want you to in your mind, kind of think through this image. If we think about every one of these outputs, pixels, as a neuron, its output is a weighted combination of 9 inputs here, right? And those 9 inputs, in this case, are weighted by these fixed weights, 1/9, 1/9, 1/9. And that's why I drew this diagram that looks like this. Now just keep in mind that when I drew it like this, I'm showing you 3 inputs into every one. In 2D, it would be 9 inputs into every one. Right? So if this was actually an image, there would be 9 inputs. And so I didn't draw a 2D version of a convolution in my little DAGs. I drew a 1D, okay? And if you took like a computer graphics or computer vision class, you would learn that there are if I change these weights, I actually get very different outputs. And so, averaging made a lot of sense, but imagine I change some of these weights and make some of them negative. Now all of a sudden, what is this computation doing? Instead of averaging every pixel, it's saying I want some positive scaling times these pixels over here minus the value of these pixels over here. And now all of a sudden, that's a finite difference computation. That's a gradient computation. So with these different weights, all of a sudden, my convolution is not blurring the image. It's in fact doing things like, it's detecting horizontal gradients, or it's detecting vertical gradients. Okay? And so all of these, at least in image processing, in the front half of the talk, I'm going to focus on these conv layers, which are common in image processing. In the back half of the talk, I'm going to bring up retention and transformers. But like all these convnets there are a bunch of these convolutions, largely, except the weights are not given by me. They are learned. So here's an example of like the classic ImageNet weights from a long time ago. Here are the weights of a whole bunch of different filters visualized. So this is this is an 11 by 11 convolution now. Okay, and so this is a convolution that takes 121 elements of the input for every output. And there's 96 different versions of these convolutions. And so if I take these filters by this input image, you get these different outputs. You can just say that these different filters are sort of lighting up on different parts of the image. They're sort of like detecting different features. Okay? And so I want you to think about this calculation as taking this code here and then repeating it for a whole bunch of different filters with different weights. That's the essence of what we're going to do here on something like this. And a common way to visualize this stuff is think about these n-dimensional tensors. So imagine you had an input image that's width by height. So it's width by height by 1. And then imagine I have all of these different filters that are just like I just showed you, 3 by 3 matrix of values and stuff like that. So there I have these 3 by 3 filters, and if I'm going to do num filters of them, I'm just for convenience, I'm going to stack them together in a tensor. So it's 3 by 3 by number of these filters. And so if I do num filters convolutions of this, I should get width by height by num filters amount of output. Okay. And then we're just going to repeat this process over and over and over, producing a bunch of filters, taking it through that function f, which is setting everything to clamping at 0. And then maybe actually doing some, a few other calculations, like in this case, a max pool is largely just a downsample, and so on and so on. Okay. And when you see all these fancy diagrams like this is, all this is just each one of these blocks is largely this sequence of a bunch of convolutions, or at least that's the computational meat of it. Wired up in very different ways, right? So here I have ResNet, here I have a common UNet architecture where everything decimates and then it comes back. That's Inception from Google. Okay, so at this point, all I really want you to know is that it's important to be able to perform a bunch of convolutions on an input image, and that produces a bunch of output images. And then we're going to perform convolutions on those. Okay? And that's the workload that I want you to know about. Okay? This is the point where I'd be happy to take a question or two, because a lot of you probably know a lot of machine learning. And you may, maybe have something, you may take issue with any of my simplifications or something like that. Okay? Is it okay to keep going? All right. So first of all, now let's think about how we are going to make this stuff faster. And this is a good point in this course where I'd like to sort of talk through what are our avenues. And there's 3 avenues of making this faster. One way is we take machine learning classes and we think about these architectures and we design better ones. For example, there's a lot fewer flops in ResNet and Inception than in some of the original conv layers that sort of made it big, or the convnets that made it big early in this modern deep learning wave. So significant algorithmic topology design improvements reduce the amount of memory needed, amount of flops needed, and so on and so on. Okay, so that's sort of that's one way we can go, and that has nothing to do with the skills that I teach you in this class. That would be you go take a machine learning class. and you say, you know what, the way SGD performs, I feel like there's some value in transferring information around a couple of layers with skip connections, which was one of the big innovations of ResNet. Or I don't really want a lot of convolutions. I only need a couple, but I have to wire them up in this particular way. Right? So I'm showing you an example of that's from the Inception ResNet block. They're kind of like, if you think about it, you say, well, what do I need here? I kind of feel like I want a couple of paths of 3x3 convolutions to do this amount, features of this spatial extent. I need a few cascades of them. Maybe I might have one path that has features of a wider extent. If you're a designer of these networks, you think about those sorts of things, right? And if you're a designer of those networks at Google and they say make these things fit on a mobile phone, you hang around for 2 years trying various combinations of this stuff and come up with an architecture that looks a little, this is a mobile net. And this is, we're back in 2017 and stuff, so this is starting to get kind of old now. But the point was that there was a small team, a person at Google, that tried different combinations of I need this many filters and I need this many layers and so on and so on. And they came up with this design. If you look at it, here's the size of the filters, 3x3 versus 1x1. Here's the number of those filters. And if every single time you do a sort of a downsample, this is the output tensor sizes of all of those layers. And first of all, actually, if you take a look at this, is there anything alarming? Given what you know in this class? Yeah.
That's a lot of work for a small phone. Like just
I see. Yeah, I thought you meant like figuring this out was a lot of work. And I'm like, yeah, it was, and they tried to automate this guy later, but that's a different story. Well, I mean, a couple of things that I see is, first of all, if you look at every one of these layers and you look at the output size, and at first you might look at, well, it's just a 28 by 28 image. That's pretty tiny. Should be nothing. And then if you think about, instead of red, green, and blue at every point, you think about there actually being 256 channels or 512 channels. You're like, there's quite a bit of output between each of these layers. Like, that's not fitting in cache anymore. The other thing that should be like a little surprising to you is just like, crap, 7 by 7. How the heck are you going to SIMDize this thing, right? There's some weird numbers here to actually make fit in a modern SIMD processor. So it very well could have been the case that, like, might as well made that 8 by 8 because you would have gotten a bunch of stuff for free. But anyways. Okay. So the point of this is, first of all, a lot of systems classes take the architecture that is the best architecture of the day as a given and say, let's try and optimize that. And I just want you to keep in mind that on the algorithm side of the fence, there's constantly massive innovation and iteration. So here are some examples. This is again from like image classification, kind of the task that kind of got a lot of this started, at least. And these are different networks that people designed in the research. And like you can think about, and so basically they're getting more accurate over time, right? So the y-axis here is accuracy, how well they classify objects in an image, or what's in an image. This graph down here is accuracy, like 90%, 91% per flop, per like expense. And this is where we were in the early days. And these networks over here may not perform all that much better. Some of them perform better, but like this VGG19 is already all the way over here. These better topologies are actually efficiency, right? And that plot over there is actually just like a 2D diagram of accuracy per unit cost. So you want to be on the top left of that diagram. Okay. And so if I look at just a couple of these things, I pull them out, and I pull them out from like basically a change every year. The accuracy was largely, at this time, was kind of about all the same. But if you look in both like the number of weights, so the number of filters, more or less, or the size of those filters, there's a dramatic drop in the amount of memory that's needed to store this model. And there's almost a commensurate drop in the amount of computation math needed to perform it. So that's about 25x from algorithms in a span of about 4 years. Hardware is not going to get 25 times faster in those 4 years. Okay? So if you had designed an algorithm for this network, you would have been, you might have been pretty far off what is the right algorithm for this network. Okay. So I just want to start by making sure everybody understands that that's out there. And so if you were a good machine learning systems engineer, you have to be tracking the state of the art in these things. And with these big large language models and transformers, there's this huge push to build bigger and bigger because of the scaling laws, right? And there's definitely a reason for that. But at some level of quality, there's all these chip companies out there that were building these big chips because they're like, well, today's LLM is huge. And what's been going on in the last 6 months or the last 12 months is with Llama and all these other things, it's about once you get something that works to your satisfaction, the engineers can come in, or the ML engineers can come in, and they can shrink the hell out of these things, right? So it makes a complicated design problem of what should you be designing your systems for. Okay, now approach 2 is highly relevant to us in this class. Is at some point you say, this is the architecture, this is the topology that we're going with, and we need to make it execute well on the machine that I have. And in this class, the machine that you have would be a multi-core CPU or a GPU. Okay? And I don't mean in this class, I mean 149 in today's lecture. I mean a multi-core CPU. So here's me taking my 3x3 convolution slide and just changing the C code a little bit to talk a little bit more about what's going on. So first of all, it used to be 4 loops now. Now it's 7. So it's let's look at the I and J first. For every output pixel, for every filter, we need to iterate over the input pixels I and J. And also, okay, so one thing I haven't said that it's input filter, we're iterating over all input pixels I and J, but that input image, the input, has multiple channels of depth. Right? So you're actually iterating over all pixels and all RGB or all 512 channels and so on and so on. So this is the convolution. It's a 3D convolution largely, or it's a 2D convolution on a 3D input. For every filter, for every output pixel, and then the outermost loop is the loop over batches of images. So often we'll actually do multiple things through the network at once. That's your batch size. Okay, so 7 loops here. 1, 2, 3, 4, 5, 6, 7. And this wouldn't be hard to implement at all. Like you could just go code this thing up, code it up in C. It probably wouldn't perform that well, but it would be a correct implementation. Okay. So now comes into the association between convolutions and vector algebra. Okay. So let me show you a quick hack. So you can go to NumPy, you can go to your favorite library, and you can call matrix multiplication. Right? And you assume that whether it be MATLAB or Torch or NumPy, if you call matrix multiplication, someone has taken the time to implement it well. Right? So there's kind of this reduction of if you can boil something down to matrix operations, maybe you're in reasonable shape. Okay? So it turns out that it's really easy to think about a convolution as a matrix multiply. And let me tell you how to do that. And this is actually how some of the earliest conv layer implementations were implemented back in the days of of pre-CUDA systems and stuff like that. So imagine that I have my input image here. This is my input image, x and y, at every x and y. And imagine I have my convolution, and let's say it's a 3x3 convolution, so there should be 9 weights. Make sense? And then what I'm going to do is I'm going to say, well, every output pixel is just the dot product of these weights and some subset of the input pixels. So I'm going to copy the appropriate input pixels into a matrix here that is width by height rows and 9 elements across. Okay, so this is 9 times bigger than the original image. Can you see that? So I'm just going to copy data in so that the output pixel, the output row, or the dot product of this row and this row is the first pixel of the convolution. And so what I'm showing you here on the slide is what values, how I would copy values in. And then let's go ahead and think about the next row, and I'd copy these values. And it might be the most clear if I get way down here where there's no boundary conditions. And so if I'm going to produce pixel at 1, 1 coordinate of output, output pixel, I'm going to need those 9 pixels from the input. So I just copy them in right here. And the output of the convolution is just going to be the dot product there. So I hope you can see at this point that with the appropriate padding and data duplication, I can implement convolution as a matrix vector product. Right? Okay, so check your understanding. Now imagine I want to do a convolution with not just one filter, but I want to do a convolution with many filters. How does my setup change? Go. So this vector, this column vector, which is the weights of one convolution, I would just stack more and more columns there, and it becomes a matrix. So if I wanted to do multiple convolutions against the input image at once, I just copy the image into this left-hand side matrix. My weights are just sitting there as a number of filters columns. And now I have matrix products. So if you give me a matrix multiplication library, I know how to populate this matrix in order to produce the output. Okay, one more check your understanding. Imagine that the input tensor is not just a single channel image. So here at every xy, there's only one value. Imagine that it has multiple values. It's a multi-dimensional tensor. Let's say it has 512 values here. How do I change my computation? Because now remember, every convolution is going to be 3 by 3 by 512. How does this setup change? Yeah.
Have more nodes making add on to 3 channels.
Okay, so this is going to be multiplied by 512. And I need weights for 3 by 3 by 512 to go down here. So I'm going to get much, much bigger matrices. Right? It'll look a little bit like this. If there were 3 channels instead of 512. If this was RGB, let's say it would look like this. Okay? So now we have, like if you give me the fastest matrix multiplication on the planet, you give me, I can produce inputs for you, or I use that fastest matrix multiplication on the planet to execute one of these conv layers. And so here's a slide or a figure that I stole from NVIDIA where they talk about this transformation. So on the left-hand side are the values in your tensors, like what you'd think of if you were using Torch. Right? So I have an input tensor X, which is width by height with C channels and batch size N. Well, that means I need a weight matrix of C channels. R and S is the 3 by 3, the size of the thing. And then I have K filters, right? Yep, exactly. So this is like common parameters for your conv layer. And just notice that this converts, using what I told you on the last slide, to matrices A, B, and C that have dimensions that are the products of some of those parameters. So this is what you would do, like if I gave you a fast matrix multiplication library. And so that matrix product, A times B equals C. C contains the result of convolving with with K filters, an input that is width by height by C, to produce an output that is P by Q by N. Pausing for questions. Okay, and as you can imagine, pick your favorite computer, Intel, NVIDIA GPUs, increasingly AMD GPUs, and you can go download a library that does fast matrix multiplication, right? And you're not going to write it any faster than them because they have, they're crazy hackers working on this at all times. Okay, so that's one way to do this. But maybe we should talk very briefly about how the heck would you even begin to implement this matrix multiplication if you wanted to be one of those crazy hackers that worked all the time on these libraries, right? So here's matrix multiplication. It's actually much simpler, right? I showed you a 7-loop nest. Matrix multiplication is just a simple 3-loop nest. And some things to think about are like, in this case, I have an m by k matrix by a k by n matrix. Let's just, for simplicity, let's just say all the dimensions are n for now so we can think through this. So if all the dimensions are n, how much data do we end up touching? 3 times n squared. And how much work do we do? N cubed work, because there's 3 loops over n. So the problem with this implementation, let's think about it for large n, because we set this thing up. N can be quite large, because n might be 512 times 7 by 7 or something like that. These might be gigabyte-sized matrices. Knowing what you know about how computers work, what do you see as the problem if I think about this innermost loop of matrix multiply? It's reading that row of A and that column of B to output one element of C. Yeah.
Across a bunch of cache lines, we're not being able to reuse that.
Okay, so and the story is a little bit different. So the question, the statement, which I agree with, is we're going to get very bad cache locality. But let's think about that in more detail. So we are reading across A, across that row. Are we particularly upset about that? Not really, because it's kind of like the most coherent memory access you can make. B, we're jumping all around memory because B is, if this is row major data, every element you touch is going to be far away in the address space and on a unique cache line. And C is actually as best as it possibly could be because I'm just reading and writing the same value that's going to sit in cache. But if you take a step back and think about your bandwidth bound problem on your homework, this is actually not much better than that bandwidth bound problem on the homework, right? Because we're going to read an A, we're going to read a B. The access to B is pretty terrible. And then we're just adding into C. So you're really only doing one math op, a multiply, or 2 math ops, a multiply add, yet you're reading 2 values. So this is your classic bandwidth bound setup. Which is a little bit weird, right? Because matrix multiplication, you just told me, is n cubed work for n squared data access. So fundamentally, it should be O of n arithmetic intensity, and you just gave me something that's like O of 1. So you gave me a bandwidth, or I wrote, you didn't give it to me, I wrote a bandwidth bound problem. Yet if I think about how to do this properly, you would tell me, oh, just put matrix A, B, and C in cache, and then the arithmetic intensity should be O of n. N cubed work for every... But the reason why I can't put A and B in cache is what? They're big. These could be gigabyte-sized matrices, right? So this low arithmetic intensity doesn't seem fundamental, but at least the way I wrote the code right now is I'm screwed. Like I'm running problem 5 essentially from assignment 1. How can I do better? Yeah, what?
Divide the matrices into blocks so that each single block can fit into the memory.
Okay, so the idea, which was just given, is the first thing is to observe that I can express matrix multiplication not as operations on individual elements of the matrix, but I can express matrix multiplication hierarchically in terms of a bunch of submatrix multiplications on blocks. Right? That's like the real key insight. So I'm going to rewrite the code, and here's how I'm going to rewrite the code. Think about everything from this for loop down as just a matrix multiplication of 2 subblocks. And so the outermost loop is matrix multiplication over blocks. So let's think about it. Let's take one block of A, one block of B, let's load them into cache, and let's multiply those matrices together. And I'm going to get an output matrix, which is a piece of C. And then I'm going to move one block over in A and one block over in B. And I'm going to multiply those matrices. And in the same way that I added in an element to C, here I'm going to add in the resulting subblock result into the block of C that I'm computing. Okay? So what's my arithmetic intensity now? For every one of these steps, if I kind of think about, like, I should have highlighted this. if I think about now the computation being a sequence of these steps, what is the arithmetic intensity of this? It's just matrix multiplication on block sizes of B, or block size here. So the amount of data that I have to load is what? B squared, on the order of B squared. And the amount of work that I do is B cubed. So my arithmetic intensity is this. It's not N, but it's B. So the greater I make my block sizes, as they go to N, as the block sizes go to N, I get arithmetic intensity of N. As the block sizes go down to 1, I get arithmetic intensity of 1. So my thinking of how to choose the block size should be I want as big of a block size as possible. And what do I actually mean by possible here on this statement?
It's like the max of the cache.
Yeah, I cannot make my block sizes so large that I start getting capacity misses on my cache, right? So you would know your cache size, you would pick your block size so that you could fit a block of A, B, and C in cache, and then you would structure your code this way. And I think we focused on this example in the CUDA tutorial last night. But if you don't, the code on the previous slide and this slide will take you all of 15 minutes to write, like in C. Pop open a C compiler and do it. Make your matrices on the order of many megabytes or a gigabyte. You'll be on the order of 1,000x different speed. It'll be insane how much faster the difference is. Right? So if you ever implement matrix multiply like this on big matrices, you are running at your bandwidth limit. And if you block, you'll be going much, much faster.
Yeah, so how are those blocks stored in cache lines? Are they stored by row parts or column parts?
It's a great question. Let's answer the question first let's think about how that would work on a normal CPU. On a normal CPU, a cache just, all it does is store lines from the address space. So even though, let me go back to my figure here. Think about all of the cache, let's just say that I choose a block size that's cache line size by cache line size. Okay, just to make this description easier. The cache lines that I need for that block of A are not contiguous in the address space, right? Because of the way they're stored. So I'm going to just load those cache lines, and the cache is going to figure out a place to put them, right? And when the processor issues a load instruction to whatever address that this is, the cache will map that to the location in the cache where that cache line is stored. So on a CPU, the whole point of the cache is you don't manage it as a software programmer. And you could get in trouble if, for example, Intel's algorithm for mapping addresses to cache lines doesn't allow, like if there are collisions, two very different cache lines end up in the same spot of the cache, that could cause some problems and you might not get the performance you expect. You go, oh shoot, how did this happen? And then you might have to sort of change your data layout or something like that. But you could also consider that shared memory on a GPU, we would do things a little bit differently. We would literally have our CUDA thread say, please load that block from the address space and put it in a contiguous allocation in CUDA shared memory. And that's the difference between a cache and what a CUDA shared memory is more of what's called a scratch pad. A scratch pad is a different address space. A cache is just an implementation detail on the same address space, right? But either way, let's assume that we can fit those blocks in cache.
Yeah, you mentioned the number of memory accesses here is b squared.
B squared for every sub-step.
And that subset just corresponds to loading in each of the b squared elements in the A block and the B block.
That's right. We're going to load b squared elements here. We're going to load b squared elements here. And let's just assume that, let's ignore the reuse, and we're going to load b squared elements here. Then we're going to do a matrix multiply with those matrices, and we'll do b cubed work. So we're doing b cubed work for every b squared I/O. Make sense? I thought I saw one more question. Okay. And by the way, remember any modern system, or at least the CPU, is going to have an L1 cache, it's going to have an L2 cache, it's going to have an L3 cache. You might even block into your registers. So, my code can start adding loops pretty quick. Right? All I'm doing is now choosing different block sizes. So that block size, I could say, give me some blocks that fit in the L3 cache, and then let me partition that into a submatrix multiplication of blocks that fit in the L2 cache, and so on and so on. You almost certainly probably want to block for the L1, but like one level of blocking will get you most of the work, but maybe an extra factor or 2 or something like that could come from more blocking. Now, of course, this is an algorithm that's just plus equals blah, 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 blah. Like, I haven't even talked about SIMD yet. Right? So the multi-threading seems pretty simple. I'd probably just parallelize over the outermost loop or something like that. But the SIMD could be a little bit gnarly if again, there's professional grade hackers hacking on this all the time and stuff like that. So let's just think a little bit about the SIMD. So I decided to write this in intrinsics. Let's say that we are, and now by the way, my figures are not the entire matrices. I'm thinking about how do I multiply these blocks. So notice the dimensions are block size now. So I could think about it as, well, I should take a vector from B, an element from A, copy the element of A, that's the splat, copy that element of A 4 times, and now my dot product is actually producing multiple outputs of C at the same time. So that's kind of interesting. Now I have a SIMD version of the thing, but I kind of have to waste this splat instruction. I don't like the fact that I'm still walking through B, not in row major order. I don't like the fact that every instruction here is dependent on the previous one because I'm doing a dot product, which actually might hurt ILP and some other things. So the design space here gets interesting and complex fast. Like, for example, I could do something where I pre-transpose the block of B. And if I pre-transpose the block of B, now I'm actually just doing a straight SIMD dot product the whole time. Okay? Or there's other versions of it where I actually pre-transpose A and not B and produce transpose C and then retranspose the thing at the end. So I'm not going to get into any of the details. Like, it kind of depends on your SIMD instruction set and your machine and stuff like that. My point being is, this could easily be a 2-week programming assignment if I wanted it to be for you. And you could try all these various things. And keep in mind that the strategy, let me go back here, the strategy might be a function of my dimensions of the block size or the matrix. Different block sizes might lend themselves to different strategies. And if we go back and look at this particular network, here are your input matrix sizes, and they're all different on every layer. So if you really want a good implementation, you might use a different matrix multiplication implementation for the various layers. And if you implement only one, you're probably going to be suboptimal, like in this sort of really weird long matrices as composed to up there. So this stuff gets gnarly, and people have put a lot of work into kublas and a lot of work into these matrix multiplication routines. Now, there's also another big, if I go back a little bit, there's a big problem with this also. And I'm surprised nobody's raised their hand yet. Because I had an input image, right, or a couple of input images, and what did I do? Yeah. I basically took every element and duplicated it a ton of times in order to make this matrix. So I took a data set that might have been a few hundreds of megs and actually made it a matrix and did all this data copying to generate, maybe multiple gigabytes of matrices. And especially with a certain batch size, and actually if we think about, for those of you that have taken a machine learning class, having to keep extra information around during backpropagation and stuff like that, you're out of memory very, very quickly. Like with these little matrices, all of a sudden your footprint is like 16 gig. Or these little, intrinsically small matrices that just blow out to 16 gig. So one thing to keep in mind is that, where are we? One very modern way to do this is to say we're going to think about it like matrix multiplication, but we're going to go get the data from the original sources on demand when I'm constructing these blocks, right? So the actual data will be, so if you look at this is a matrix multiplication. For simplicity, I didn't block it here. For simplicity, it's not blocked. It's just normal matrix multiplication, but instead of the element A coming from x, I times width plus j, it comes from this accessor which does all of the math to figure out what is the location in the original input tensor, not the matrix, that would have stored the value that I need at this matrix cell. So it's matrix multiplication, but not accessing the matrices that I would have created. It's accessing the original tensors. Okay? So in other words, they're burning math in this inner loop to compute that address as a function of the tensor dimensions in exchange for not decompressing the data into these big matrices. Okay? So this is something called implicit matrix multiply, in that it's not actually operating on matrices that are this size, even though the loop structure is if it's operating on matrices of that size. Yes?
So there will be cache inefficiencies now, right? Because you have not put up a contiguous block.
You're correct. So this dot product that feels like it's iterating over a line of a row of the matrix is actually iterating all over that original image. But don't be too worried about that, because remember, that would have sucked anyways. This is gonna be blocked. So you should think about these accessors you bounce all over memory when you're bringing that data into shared memory or to cache. Once it's in shared memory or cache, you flatten it out and make it dense. And then you run your subblock matrix multiplication on the dense stuff. Okay. In other words, you have to copy data from DRAM into cache. That's the point at which you do your copy. You don't copy it into a new location in DRAM and then bring it in. There's a big difference. Okay. So that's what you'll see if you just see this implicit GEMM. And by the way, just one more thing is, the other thing that good implementations do is all of this math that goes from width, height, number of tensors, and batch size to an address. If you want the fastest implementation, is you pre-compute that math. And then you actually make this a lookup table. So you actually burn a little bit of memory to get back the addressing calculations, which actually can be non-trivial for larger tensors. So NVIDIA has this library called Cutlass, which if you want to be a pretty elite hacker and not go all the way to implementing, matrix multiplication by yourself in PTX on GPUs, you might lose Cutlass these days. So Cutlass gives you access to very fast matrix multiplication libraries that fit in shared memory, that have the ability to go pull the data from various locations and things like that. So this is short of writing your own good CUDA assembly and on the low end and using TensorFlow on the high end, Cutlass is something in between. You're like, I want to implement my own deep network because I want a really small network running as fast as possible on an NVIDIA GPU. You'd use something like this these days. This is not a very user-friendly library. Okay. Now, just keep in mind that all of this, at least on a big CPU or on a big GPU, is running on this thing that's quite large, right? So each of these little SM cores might be kind of cranking on a subblock matrix multiplication. You still need pretty large matrices to fill up this GPU, right? And that's why when batch size is 1 in machine learning, your performance can go down. There's just not enough work. And so here are some plots where I'm varying n. And remember, P and Q were the output size. R and S was the filter size. So 1 by 1, 3 by 3, 5 by 5. And just notice that you've got to make, for different batch sizes, you've got to make those output image sizes somewhat large before the performance of the GPU has enough work to actually keep itself busy, right? So when people are saying, gosh, with these big neural networks, I can only run batch size 2 or 3 or something like that because I'm going to run out of memory otherwise, they pay for that in performance because as these things get a little bit smaller, you're not going to be able to run this big processor at peak rate.
Just the y-axis here is
Is throughput, yeah. Floating point tera operations per second. So higher is better. These 3 different lines are 3 different model sizes, different output tensor sizes. P and Q is the X and Y dimension of the output tensor. And then here, this is not relevant these days because these wide convolutions don't really exist. But this is just saying if you're using wider convolutions, you do more work, and that work fills up the GPU more quickly. So the graph on the right, I think, is on the left is probably more applicable today. Okay. Now, of course, I can also just go back to my original blocked conv layer, which here's my C code of my 7 loops. And I just did 15 minutes on how hard it is to optimize a 3-loop version of matrix multiply. You can also just say, go at it, start blocking these loops. And so, if you want to just do a direct implementation and do it well, you can definitely do that on your own as well. And these days, and I'll get into this in a second, there's a lot of interest in just giving this information at a good compiler and saying, hey, good compiler, you come up with the blocking strategy for me, right? And that's things like XLA at Google or this new Triton thing from OpenAI. They're trying to do that, but in general, I still think these core inner loops are still kind of best done by humans by hand. Let me just show you a few other tricks which are actually pretty interesting. And so keep in mind that, so remember I said that a convolution, here, ignore all this, we can think about it as a set of weights as a right-hand side in a matrix vector product against a matrix that comes from the elements of the input tensor. And if you look carefully, you're like, you know what? So let's think about this as M1 plus M2 plus M3. So M1 is just this product, M2 is this product, M3 is that product. If we look carefully, there's some common sub-expressions in here. And we can exploit those common sub-expressions to do some partial, to do some early math and then actually compute the outputs as a function of those common sub-expressions. So in this example, this is actually the essence of what's called a Winograd filter. So you might have heard of a Winograd convolution. Is I've taken direct convolution. I used to do 6 multiplies and 4 adds. Now I'm actually doing far fewer multiplies and a lot more adds. Now, whether or not this is a good trade-off is going to depend on your machine and stuff like that. But there are ways that I can algorithmically start moving symbols around and do different amounts of math. Probably the most common one would be, for those of you that are from EE or know anything about signal processing, you know that a convolution can be expressed as a Fourier transform, a basic pointwise multiplication, and a Fourier transform back. And that fast Fourier transform is basically employing techniques like this where we're exploiting common sub-expressions to remove work. So you can think about this as applying Fourier transform kind of ideas. Okay, so all of the big vendors have their own deep learning libraries like CUDA or Intel's One API these days. And if you move up the stack and use Torch or TensorFlow, all of you or many of you are probably familiar with the library of different layer types that you have available to you. So we've talked about conv2D. That's the one we've talked about here today. But other ones are a little bit simpler, and so you get this library of optimizations. And if you use this in Torch or TensorFlow, these operations under the hood get compiled down to cuDNN and these lower level vendor specific libraries. Okay? And if we pop open the API of cuDNN, which is NVIDIA's core library, you just kind of look at the parameters to, this is cuDNN convolution forward. This is the forward pass of a convolution layer like we just talked about. And you see a bunch of interesting algorithms or parameters to that thing. It's not just tensor X weights W and output Y. You get like this descriptor to the input tensor. You get choices for what algorithms you want to use. And if we look at the algorithms, this should actually make a little bit more sense now. So let's go look for, here's implicit GEMM. So GEMM is general matrix multiplication. The default algorithm is implicit GEMM, which says take my tensors, treat the conv layer as a big matrix multiply, but don't ever actually make these big matrices. just do the loop indexing as you're doing a matrix multiply to look up the values. Right? Here's forward algorithm direct. This would be like, oh, just use your blocked version of my 7 loop nest to actually directly do the convolution. Here are various other ones like, here's GEMM, but not implicit. So this actually says copy the data into these big matrices, and please do it as a normal matrix multiplication. So you have a lot of these options. These Winograd options or these FFT options are saying, oh, we want you to transform with an FFT and so on and so on. So you basically just tell the API, given what I know about this, here's how I want you to do it. Okay, so what we've talked about so far is how to implement matrix-matrix multiplication, which is basically how to implement a conv layer. By the way, like a blocked MLP or a fully connected layer is also a matrix-matrix multiplication, so it applies to that as well. What we have not talked about at all is the fact that there are multiple layers back to back to back. And there can be hundreds of these layers back to back to back. Now keep in mind that I just told you that the output of one of these layers is a big freaking matrix, a big freaking tensor that could be tens of megabytes or hundreds of megabytes. And let's just think about the basic sequence of a conv layer. We might do this big matrix multiplication and output a width by height by n by k output tensor. We're going to store that in memory, and then we're going to bring it right back in and do something like add in the bias. And then we're going to store that in memory, and we're going to bring it right back in and do a max pull. So this tensor is going in and out of memory over and over and over again. And for these, conv layer might be blockable, but scale and bias is not. The only thing you're doing is multiplying every element by a number. And max pool, there's not a lot of math in there. I'm just taking every 2 by 2 region of the tensor, computing the max and outputting that. So these things here are severely bandwidth bound. Severely bandwidth bound. So we would love to be able to just kind of do all this in one shot and then send the tensor out to the rest of to memory. So here's an example of it's very easy for me, if I knew the scale and bias that's happening, is once I get done with the matrix multiply, I should go ahead and scale it and bias it. And that just saved me hundreds of megabytes out to memory and back. Here's an interesting thing is, how would you rewrite this code if you wanted to do the max pool all in line here? It's not that hard. It would make for some gnarly code, but conceptually it's not that hard. How would you do the max pool right on the spot? Yeah.
You just need to ensure your block size is like a multiple of like.
Yeah, so imagine this was blocked. If it was blocked, I would have produced a block of output sitting there in cache. I should do my max pool right then before I send it out. And then I not only save the store and the load, what I store is 4 times smaller than what I produced anyways. So there's a huge win there. So it turns out that this stuff, really matters, and that's when your layer types get kind of gnarly. And without any compiler support, that's when TensorFlow start having API entry points that were called like com2d fused batch norm, power of 10, or something like that. Like you just start seeing this API that just gets huge, because they're like, well, this one's like a really slow sequence, and we need to make a special case for that. Nowadays, people are hoping with things like JAX and Triton that if the compilers, given knowledge of these operations, can do some of this fusion for you. But it's still not great. It's still not that great. And let me tell you why it's not super great. I want to tell you about a cool little trick that was invented here at Stanford about a year and a half ago now that significantly improved the performance of these transformer layers in large language models. And if you take a step back, this trick is basically something that any of you in 149, had I given you a transformer layer, you would have looked at it and you would have gone, yeah, you should definitely do this. right? And had you done this a year and a half ago, you would have been the talk of the town, in the machine learning Twitter sphere, right? So I want to talk very quickly. I'm going to move away from these convolutional models. I'm going to talk about these transformers, and I want to talk about sequence-to-sequence transformers. So one, like for example, the input might be a sequence of tokens, maybe a sequence of words, and the output of the model is to produce the next word, just auto-regressively. Okay? The application doesn't matter at all. What does matter is the workload when we look into the key part of this neural network, which is this box, which is called attention. And I'm not going to get into the algorithms of attention at all right now, but I'm just going to tell you what the workload looks like. The input are a bunch of tensors, 3 tensors, Q, K, and V. There are some, I could give you an interpretation of this as a query, this is the key that the queries match, and this is the value. So you could say, hey, for every element in my input sequence, I'm going to think about that as looking up in a database of what other tokens match. And based on what matches, that's going to influence the output. But just think about it for now, as I have 3 embeddings. I have 3 vectors, Q, K, and V. They're n-dimensional arrays, and at every point in that array, think about there being a d-dimensional embedding. Okay? So I didn't give you the dimensions here somehow, but this is n by d, this is n by d, this is m by d. And this attention layer basically is just going to compute interactions between queries and keys. So in other words, we're going to take an outer product of the query vector Q against the key vector K. And if these are n by d, my output is going to be an m by n matrix. So I'm going to do a matrix. I'm going to do an outer product to produce a matrix. Then, for every row of that matrix, I'm going to perform an operation called a softmax. If you don't know what a softmax is, it does not matter. Let me tell you what matters about the softmax. The softmax of x, which I want you to think of x as the row of the vector, is just a scaling of all the elements, but that scaling depends on the maximum element in the vector. Okay, why does that matter? That matters because I don't know what the maximum element of a vector is until I've computed the entire vector. So this would be like saying compute the sum of all the elements in the array and normalize everything by the sum. Computationally, it would be equivalent. Okay? So the problem here is I do a matrix multiply. I produce an m by n matrix. Then for every row in the matrix, I got to compute the max element. And then I use that max element in a new computation to do another matrix multiply. Or in this case, sorry, a matrix vector product. So let me diagram this out for you. I have Q and my K vectors that are n by d. I multiply them together to get a matrix here that's n by n. And by the way, n is large, because if we think about sequences of tens of thousands of tokens, we're talking about n squared on n equals 10,000. This is a huge multi-gigabyte matrix. Then for every row of that matrix, I'm going to compute the softmax, which again, if you don't care about softmaxes, just think about I'm going to compute the sum of all the elements in the vector, or the max of all the elements in the vector. Okay? So I normalize all the rows by that sum, and then I do a matrix vector product in order to compute the final result. Okay? The problem is that this matrix is huge, and so you could do blocked matrix multiply, so you can compute that matrix very efficiently, but you still have to store it out to memory. You have to bring it back in row by row to compute the softmax. You have to bring it back in again to compute this matrix vector product. And I'm not showing you a few other steps. There's some things that people do with like masking this thing and stuff like that. You got to bring it in like a bunch of times. Right? That's where the compute is in these transformers, or at least the cost is in the transformers. There's no compute actually, which is the problem. Okay? So here's the trick. The trick was, is there any way we can do this whole sequence block by block? You just told me how to do a max pool in the middle of a conv layer. The question is the same here. Is there any way that I can fuse through this softmax, which looks like something that needs every element of the matrix before I can go any further? And some folks just kind of looked at it, and said, okay, so here's again the math of the softmax, which is for every element of the vector x, we're just going to scale, we're going to raise e to the power of x scaled by the maximum element in the vector. So I have to compute that max, and I have to compute the sum in order to know how to scale. Right? That's basically, okay. And it turns out that you can factor this and compute it block by block. Okay, and like the details of this, I think we should take offline. But the general gist of it is, let's think about x as a first half and a second half. So here's the first half, here's the second half. And if I think about what is the max of vector x in terms of maxes of x1 and x2, well, the max of x is clearly the max of x1 and the max of x2. So, this can definitely break down. And it also turns out that computing this f of x, well, all I need to know, if I knew the max value, I can compute f on the first half, and then I just scale it back up by something we already know. Okay. Now, I don't expect this to be followed in real time, but in 10 minutes of math, and you just kind of notice that inside of this term, there's an e to the x1. So these are going to cancel, and you're going to end up with, it'll all work out. The point being is that softmax can be computed in chunks if you just keep a running sum of max. Okay? And as a result of that, I can fuse through this whole thing. So I can compute the matrix multiplication, I can compute the softmax, and I can compute the final matrix product by loading a block of Q, loading a block of K, loading a block of V, computing the submatrix multiplication, computing the softmax on a chunk of the whole row, which is a row of the submatrix, then doing the matrix multiply, and then accumulating into O. So all of a sudden, my memory requirement shrunk from n squared to block size squared, which means I can fit much more data on chip in a GPU, which means I can run on much longer sequences, and because I'm not bandwidth bound in some situations, I can run faster. So the speed improvement was modest, I think like a few small constant factors. The memory footprint was enormous, and that moved us from sequences of length 8,000 to sequences of 32,000 and stuff like that. I believe GPT-4 is enabled by an optimization like this. So this is your basic producer-consumer locality optimization. You can imagine it would have been hard for a compiler to do the mathematical analysis to figure out that this was possible. But some folks in the group did that. And once you know how to chunk that softmax, then you can chunk through the whole thing, and all of a sudden, it's the equivalent of just reordering some loops here or there. And it's a very big change. Okay. So these are the types of stuff that matter the most, once you have a good matrix multiplication implementation. These are the types of things that are pretty funny. I actually alluded to this before. About 8 or 9 years ago, people were like, well, you've got a fuse, but we don't really know how to do it. So we're just going to have those people that implemented a good matrix multiplication are going to go ahead and implement you a good fuse batch norm into the matrix multiplication, or fuse resize and pad com2d and get a coffee at the end of it. That's basically what was sort of popping up. CUDA has had this sort of very templated sort of fusion capability, like any convolution operator followed by what's called a pointwise operator. A pointwise operator is something that just is like a map, followed by another pointwise operator. Anything that fit that pattern, they said, okay, we'll try and fuse the pointwise into the matrix multiplication. Given the fact that a great solution for max pool and other stuff was proposed in 5 seconds, this is not intellectually that hard. What is hard is to do it on arbitrary tensor programs. And so when you see these frameworks out there, like JAX is actually a pretty nice, sophisticated one right now. They're now starting to analyze your tensor loop nests and stuff like that and go, yeah, we see how we can fuse this right in, and we can generate that code for you. So stuff's getting better. It turns out that you need both. You need an excellent implementation of conv-layer and matrix multiply, and then you need excellent smarts so that everything else on the deep network, it being bandwidth bound, doesn't slow everything down. You need both optimizations to have a good network implementation. Just as I finish up, I want to talk about, there's just a whole bunch of other stuff out there. Like the next thing you do to speed things up is you stop using regular precision math. You go to lower precision math. People are pushing this to the extreme. I think NVIDIA GPUs are now starting to muck around with about 4-bit precision math these days. So the space of techniques is, first of all, you want to start with good algorithms. Like, if you're a systems person and you ignore algorithm innovation, you will get left behind. And there's a huge number of startups that are being left behind because they saw this curve of everything bigger, everything bigger. And I think that was dumb. Then you need to take 149-like principles and good compilers principles and optimize these things so that they run well on modern hardware. We didn't talk too much today about approximations like low precision and sparsity, but that's out there as well. And then the last piece of the puzzle is what hardware you run this thing on. So let's close up in the last minute and a half on this. Given what you know, why would we say that a GPU is a good platform to run these deep neural network computations on? What are some properties?
Parallelization.
Tons of parallelism. These are huge matrix multiplication operations. What else?
Has a lot of compute.
Has a lot of arithmetic intensity if you do it correctly. Yep. And so there's a lot of good algorithmic, good ordering optimizations to get the arithmetic intensity so we can use all that compute.
All of the weights are applied to each input, so it's very SIMD.
So we got a lot of SIMD capability, and we already have these processors that had a crap ton of ALUs on them for graphics, so they happen to be right in the right place for the right time to do machine learning about a decade ago, right? So that's why everybody loves GPUs, okay? Now, the flip side is, why might GPUs be a suboptimal platform for DNN evaluation, given that a GPU is an arbitrary general purpose processor? And most of this work are these very simple matrix multiplication, maybe matrix vector multiplication operations, right? So we're going to have a whole class on this, but I want to hint at it right now so that those of you taking 229 or maybe when you get around to your assignment, is what was the motivation of a SIMD instruction? Why do architects put SIMD instructions in a processor? That's correct, but so what? Why not just build a whole bunch of little processors? The idea is to amortize non-math work, instruction stream control, data access, whatever, across that same operation. Okay? And we don't have to stop there with a SIMD instruction. We could add an instruction like a dot product. It'd be super helpful for a matrix multiplication computation, like a 4x4 dot product. Do 4 math ops and add them together. Or we could actually say, how about an instruction that does a 4x4 matrix multiply? Like a little matrix multiply. I know how to use that because I know how to break down big matrix multiplications into that. Okay? So the key principle here, if you're an architect, is you want to amortize all of the overhead of running a program over the biggest math operations that you can think of. And here are some examples of the magnitude of that overhead and energy efficiency. So compared to, and these are NVIDIA's estimates, so they have a vested interest in making deep learning accelerators like TPUs seem very inefficient or not so efficient. But they said if you just run adds and multiplies on an NVIDIA processor and you do your matrix multiplication with that, you're 2,000 times less efficient than if you built custom silicon to do that matrix multiply. If you make a couple of bigger operations, like just 4-component dot product, you're all the way down to like 500. Only 500x more efficient. If you give yourself an instruction that's a 4x4 matrix multiply, because that does a lot of work, right? That's 64 ops in one instruction. You're all the way down to maybe only 30% more inefficient than these things. So these NVIDIA, their reaction was, in addition to math units for adds and loads and all your standard math, they have this thing called a tensor core off to the side. What that tensor core is, that's a fancy marketing name for all it is support for a special instruction that does I guess nowadays it's like a 4x8 by 8x4 matrix multiplication. It's like 128 ops. So if you write your code in terms of your sum matrix multiply, just going, do your 8x4 matrix multiplication, you have access to Your CUDA cores give you 19.5 teraflops of floating point math at 32-bit precision. If that's math that can be phrased in terms of matrix multiplies, and you can do it in 16-bit floating point, you get 300 teraflops of compute capability. It's an order of magnitude, more than an order of magnitude, more peak compute on that GPU, just in basically ALUs that can only do a matrix vector, do a matrix multiply. That's what a tensor core is. It's just a fancy instruction, and that's NVIDIA's reaction to what we'll talk about later, like TPUs and other accelerators, like things like this. So that's your like little crash course on modern optimization of these networks, and hopefully allows you to kind of situate yourself in the space of all these different solutions that are out there, spanning different fields. You know, the algorithms people are contributing, the software compiler and 149 people are contributing, and the hardware people are now contributing as well. So it's a very, very interesting cross-cutting space. Cool. All right.